Hello, my name is Thorsten Höffler from ETH Zurich, and today I have the honor to co-present with three different presenters from three different institutions our work on weather and climate simulations in Python using GT4Py and the data-centric Python framework. So the three institutions are the Scalable Parallel Computing Lab, my lab at ETH Zurich, as well as the Swiss National Supercomputing Center in Lugano in Switzerland, as well as the Allen Institute for Artificial Intelligence in Seattle in the United States. But let me get started right away to motivate why we need a different view on high-performance computations than a couple of decades ago, where we were all compute-centric, essentially. Here, this slide is from NVIDIA's BuildALI, giving us a little bit of the physical background that data movement is extremely expensive. So we can actually see here that just performing a computation is about 20 picojoule, but moving data across just 20 millimeter at the bus is already a factor of 10 more. And now you can look at all these different scary numbers here, like off-chip, efficient off-chip links for moving data or moving data across the whole chip, which is then already in the nanojoules. But the high-performance computing community has actually recognized this quite a while ago and got together to write a paper about how do we actually work with data locality abstractions in high-performance computing systems? Because now we don't really optimize for computations anymore. We do have to optimize for data locality to minimize data movement on-chip, off-chip, and even in the system. So this is the most important goal today. But the question is now, coming from the high-performance computing community, how do we make this approachable to a wider audience where it's really about productive high-performance computing? In some sense, it's a little bit inverted. In high-performance computing, we usually care first about performance and then productivity, but now in the newer environments that are mostly Python-driven by high-productivity languages, we may care equally about both, or we even may care more about productivity than about performance. Because after all, productivity may be saving us more money than getting the greatest performance out of it if we only work on a couple of hundred GPUs. But now, what is the fastest growing community to adapt this kind of mindset going towards high performance, but still, high productivity, but still high performance programming? And what immediately comes to mind is the deep learning, machine learning community driven by the frameworks TensorFlow and PyTorch that are both fundamentally built on the Python language. But let's go a little bit forward. What do we mean by the Python language? Well, by the Python language, we really mean NumPy, in the sense that NumPy is the language or the subset of the Python language used in scientific computing. And now, in order to understand its performance, we would need to compare different NumPy optimizing frameworks. So what we did in my lab is actually develop NP-Bench under the lead of Alex Nikolaos, who implemented all kinds of different kernels from various different domains, where we can really investigate how good NumPy codes perform on real hardware with performance metrics, but also productivity metrics and the various different frameworks. So why do I tell you about this? Because I want to motivate you why we are going to look at the DAIS code or the DAIS framework in a couple of minutes. I don't have enough time to show you the whole results. You can look at the paper yourself. But what I want to show you is just the upshot where we really see about 10x or more than 10x speed up over the NumPy baseline for computing NumPy codes, and also faster than all the other NumPy optimization frameworks. And the remainder of this talk is going to apply this to climate and weather. If you are not convinced yet why you should try DAIS, well, actually, we did get the Gordon Bell Prize in 2019 for a large-scale code that ran on the world's largest supercomputer, also in conjunction with the DAIS framework and with DAIS ideas. But again, today we are focusing mostly on climate codes. So just to give you a little bit of the high-level vision of what DAIS is, well, we start from a Python code, which is, of course, an imperative code. That code is going to be translated into a parametric data flow representation. So line by line, somehow we extract the parametric data flow, and we could look at details. But again, in this short overview, I don't want to get too much into details. I just want to motivate you to give you a very rough understanding so that you can follow the remainder of the talk. So specifically, the overall vision of the framework is to decouple the domain scientist from the applied scientist that translates the domain scientist's ideas into code that can then be optimized by a performance engineer or a code ninja to be executed on various target architectures like GPUs, CPUs, GPUs, as well as FPGAs with a little bit of a runtime. The key idea is that we have very small number of source lines of code for the domain scientist, very high productivity, very simple, really Python as we know it, Then we have reusable code for the performance engineer, and then we have thousands of auto-generated code lines that nobody really wants to look at, but of course the architecture needs those to execute efficiently. So with that, I give you just a little bit of an overview of what Days is here. We have various front ends, we have various backends, and of course it's easy to implement your own front end as well as your own backend. In fact, this talk could give you some inspiration how to do this, as we will see in a couple of minutes. Just to introduce the remainder, it's a true team project. Linus Groner from CSCS developed the grid tools GT4Pi front end for Days, and he's going to talk about this for the next couple of minutes. Tal is actually going to talk about GT4Pi Days integration with a little bit of a demo that you can see how it really works and also the tooling around it. And then Tobias from AI Square is going to talk about the FV3 prototype and initial results that we get your mouth watered about the performance results that you could achieve for climate and weather codes. So I'm handing on to Linus.
Thank you. So to explain how we connect performance portability and productivity in the GT4Pi domain-specific language, let me show you an example. So this is a NumPy code computing a diffusion. And we can notice a number of things. For example, the indices we use in the in field are not the same ones as in the other field, despite them referring to the same grid point. This is due to the fact that the in field we read at an offset, which means we need some extra lines at the boundary, which you need to compensate when indexing. We also put for loops in the order I outermost, j, k innermost, which we could have instead just put in any order we wanted. We have also put the lab field and the out field computation in the same loop nest when we could have split it up instead. There are more choices that can be made, and each one of those may lead to a rewrite of an entire code base. So here's the same example in GT4Pi. What we do here is instead declare what you want to compute and not how you want to compute it. So a few syntax elements that are not entirely obvious here are these field annotations, which mean that these are 3D fields. The interval just indicates to which vertical layers the stencil is to be applied to, and computation parallel means that they can be applied to these layers in any order. So what we see here is that we don't have these loop nests anymore. We also have the same indices everywhere. And this is because based on these relative offsets that we see here, we can just compute all this information in the background. It doesn't need to be specified by the user. Also, all the implementation concerns that we had before, they can be chosen by the pipeline and they will make the right choice for you. So the idea is that you write one stencil and then let GT4Pi decide how to handle it for a target architecture. This is done by this decorator here. So this puts the function into the pipeline, and by selecting the backend here, you indicate for which target to compile this to. Currently supported target hardwares are x86 CPUs and NVIDIA as well as AMD GPUs. So GT4Pi is a domain-specific language for weather and climate. In weather and climate, the main computations are 3D stencils and vertical solvers, and restricting to these lets us more easily optimize and lets us make things implicit, which leads to less code clutter. Doing this in Python lets us also smoothly integrate with tools such as for visualization, Jupyter notebooks, or the machine learning tools that Thorsten has mentioned before. GT4Pi is open source, developed by CSCS with a major contribution from AI2. It currently is for Cartesian grids, but there is development on unstructured grids. Regarding user codes, we have AI2, who is porting FV3 to GT4Pi. We will hear later from Tobias. And the IFS FVM models, where we collaborate with the ECMWF and ICON, where our partners are Metaswiss and Exclaim, are starting also to port their models to the unstructured GT4Pi. To understand how this connects to Days, let's look at how the compilation works. The user code will contain a collection of GT4Pi stencils, which each individually get fed into the GT4Pi pipeline. There first, we do some general analysis, which basically computes the information that was made implicit due to the domain abstraction. And then, depending on the chosen backend, we do some target optimal optimization from which we finally generate code. And now, in this talk, we look at a particular backend of the C++ CUDA category, where we use the Days data flow representation to further optimize and finally generate code. And so this works very well for small and medium stencils in benchmarking applications. But if you go to a full weather model, you will not have just stances and solvers. You will have some data control flow going on. You will have some halo exchange that will happen. We'll have reductions. And these things aren't domain specific. And so we will have to use a more general purpose tool. And for this, we basically take the entirety of the user code, feed it into this data flow representation, and use still the domain specific parts from the GT4Py toolchain and integrate it into one bigger generated code that we then compile. And how this works in actions, Tal will show you.
Thank you. So now I'd like to demonstrate the power of GT4Py and Dace working together using a live coding session. So we prepared here a simple script which contains 3 stencils written in GT4Py. So the first one is a version of horizontal diffusion, and 2 other relatively simple stencils. And these are all grouped in a single function called myWeatherApplication, which is mimicking a larger weather application. And what we can see here also is the relative simplicity of writing code in GT4Py. So it's very domain scientist friendly with the relative indices and all of the setting of the computations to specify specific types of stencils. So in order to run this computation, we have chosen the GT-CUDA backend, which means that it's going to use grid tools to run on the GPU. And in the end, we're running this 100 times. So we're going to use the NVIDIA profiler now to see how long it runs over the GPUs. So we scroll up here, we can see that there are 3 separate GPU kernels corresponding to the 3 stencils, one running a bit over half a millisecond and the others running around 100 something microseconds. So now we want to, instead of grid tools, use Dace's powerful code generator. So all we have to do is simply replace the backend here with GTC Dace GP. So now if I rerun the script and scroll up again, we can see that there are still 3 separate stencils. As before, the performance is very similar, except for the first one, which now takes only 186 microseconds on average. So, of course, when we look at these stencils and when we look at the performance, it seems that a relatively simple stencil and a much more complicated stencil run almost the same performance. This indicates a potential data movement bottleneck. So in order to optimize it out, what we have to do is optimize between those stencils. And this is where Dace and its powerful Python frontend comes into play. So Dace can parse arbitrary Python functions, which also includes calling GT4Py stencils. And in order to use that parser and optimize in between the stencils, all we have to do is decorate that function with the Dace program decorator. Now, another thing that I would like to do is to say that tempf and temp2 here are local to this function. So just going to declare them as simple NumPy arrays with the right dimensions, of course. So just going to type that. We're using double precision. And I'm going to do that for both arrays. And this is all it takes to declare that tempf and temp2 are only local to this function and they can be optimized away. Now, as weather applications are usually larger than these 3 function calls, we would like to have a starting point for optimization that is performing in a reasonable manner. So in order to do that, we can use the automatic optimization heuristics that are in Dace. In order to activate that, we can just specify auto optimize to true. We can specify that the device that we're targeting is a GPU. And now we can run it again. And with automatic optimizations, what we can see here is that the performance has tripled by fusing everything together into one kernel. From this point on, we can choose to continue the optimization process after the automatic optimizations. As you saw before on the bottom right side here, we had a popover that says, would we like to see the intermediate representation file? So what this meant was that there is an SDFG file or a stateful data flow multigraph, which represents this application. And this is the data-centric intermediate representation. Now we can view and edit that file directly in Visual Studio Code. As you can see here, this representation is quite straightforward. We have arrows here denoting data movement. We can see exact indices here. The parallel regions are denoted by these trapezoidal scopes, and computations are represented by these octagons. And if we zoom in, we can actually see them. So at this point, we can click any of those nodes and edit them. For example, changing the range or the device that it's going to run on. But we can also do more than that. So within Visual Studio Code, we have this SDFG optimization tab, which allows us to, first of all, run some transformations. But if we don't know which transformations to run, we can also perform some analysis on the data movement. So for example, data movement volume here, and also number of floating point operations. So we can clearly see here that the first stencil, or the resulting fused first stencil, is much more computationally intensive than the rest. And from here on out, we can simply select certain transformations and apply them. And with that, I would like to pass along the torch to Tobias to show how these optimizations are performed on a real weather model.
Thank you, Tal. I will now touch on how full program optimization, in our case enabled by Days, plays a key role in successfully speeding up real models. Let me start by introducing our model, GFDL's FV3GFS. The model solves finite volume dynamics on a cubed sphere grid. The cubed sphere as a grid is very well suited for scalable computation due to its regularity. But not only did we want to target a fast model, we were also looking for something that's both physically consistent and used in a wide variety of applications, like the current operational weather forecasting system. I'm not the only one claiming FV3 is very promising. In 2019, the Diamond Project studied various climate models to see how they're performing in terms of runtime and if any projections for large-scale, high-resolution runs can be made. If you look at the rightmost column here, the projected simulated days per day, where higher is better, FV3 is by far the most efficient amongst all the regular grid models investigated. Now I want to give you a quick idea of how the code base looks. We ported a model that was around 50,000 lines of Fortran code into a code base that is now 30,000 lines of Python code. The model is roughly split into 13 modules with 10 different points at which communication occurs. In these 13 modules, we find around 180 different stencils called multiple times in each time step, totaling up to 2,600 stencil calls per acoustic substep. During the port, verification was always a key point for us. In order to make sure our model behaves well, we verify our code both on a per module basis as well as on a full time step basis. Here you see a comparison of wind speeds on a realistic data set with the reference code to the left, our implementation in the center, and the differences between the two on the right. If we're also looking at idealistic use cases like the baroclinic wave, we find the model behaves just as expected. With an understanding of the model, I can finally tell you why this porting exercise was well worth it in terms of performance. And because I feel like a single data point would not tell you the full story, I want to share with you the history of the last year. The history that I'm showing here is all pre-full program optimization, just to give you an idea what problems we had to face and overcome before we switched to Days and how they potentially are no longer issues. What we see is the gray line in the bottom, the Fortran CPU reference. In blue, we have the DSL-powered CPU version of the code, and in red, we see the DSL-powered GPU results. These are the ones that we'll mostly be focusing on. You see that our initial runs were significantly slower than our reference. This was mostly due to callbacks to Python for features not implemented in the DSL. Something that we now no longer need to worry about because Days is able to turn most NumPy code directly into fast executing code within the scope of our optimization framework. Once these issues were ironed out, we were facing our next big bottleneck, kernel launches. We were able to optimize most of this overhead away and now ended up being blocked by communication times. After solving this problem, we ended up beating the reference code by a factor of 1.5x. So at this point, we were looking at various ways to increase our performance any further, and full program optimization seemed like the logical next step. So with the help of all the organizations in this talk, SPCL and CSCS, we were able to deploy a full program optimization strategy on the acoustic time step, and we were able to get these numbers. Not only were we able to beat the CPU baseline by a factor of over 2x, we were also able to beat our previous GPU codes powered by a DSL by a factor of over 20%. We can explain these very promising numbers by highlighting the three big things that Dace brought to the table. It significantly helped reduce overhead, going from 2,600 calls from Python to the fast world down to 1. It also allowed us to take the next step in optimizing communication patterns, a previous big pain point of ours. And finally, optimizing a full program rather than single stencils allowed us to be more efficient with our computational patterns. So in summary, we were able to leverage the Dace framework, a toolchain designed to allow optimization on domain-specific codes by performance engineered, combining that with GT4Pi to optimize stencils across a full matter model. FV3GFS in our case, where we applied full program optimization on the acoustic time step and were able to get speedups of over 20% compared to the pure DSL approach.